Hello and welcome to this Agilent Technologies recorded webcast. We hope you will find this webcast both interesting and valuable. If after viewing this recording you are interested in more, please go to our Agilent TM Webcast YouTube channel for more recordings or sign up for one of the upcoming live sessions at www.agilent.com/find/web_seminars. Now let's go over to the presenter.
Hello everyone. Welcome to our session with the title of Address the Challenges of Testing Low Voltage IC. The presentation will start in 2 minutes. When we talk about low voltage IC testing, actually low voltage IC is becoming more and more popular today, driven by mobile phone, tablet, and other mobile devices. However, testing low voltage IC is proved to be challenging because the current audio analyzer have potential issue in testing low voltage ICs. In this session, we will discuss these challenges and how Agilent audio analyzer deal with them. Today, we will hear the presentation by Adeline Lee. She is the product marketing engineer from Basic Instrument Division of Agilent. My name is Alvin Chang. I'm the product planner. I will try to answer your questions you may have with the WebEx. For everyone's comfort, this is a lecture style meeting, but you can send your questions in writing through the Q&A functionality of this WebEx meeting. We will do our best to answer your questions during the session, but if we cannot, we may also come back to you after the session. All the questions and answers will be published for others to see. We will keep your identity private, so no one can read your name. Please be reminded that this WebEx will be recorded, so you can review and share with your colleagues at any time. Now, without further delay, I will let my colleague, Adeline, to get you through this exciting presentation. Adeline, I'm passing the session to you.
Thank you, Alvin. Hi, everyone. Hope you are doing well today. My name is Adeline Lim, and I'm the Product Marketing Engineer for Audio Products in Agilent Technologies. Today, I'm presenting you this paper on how to address the challenges of testing low voltage integrated circuits, or better known as ICs, with the new Agilent U8903A audio analyzer with digital options. This presentation will take roughly about 40 minutes so that we can have enough time to take some questions from the audience. My colleague, Alvin Tang, will be the question and answer manager for today's webcast, and all the answers will be addressed at the end of this presentation. Let's get started by looking at the agenda or overall contents for today's presentation in the next slide. An overview of the presentation content is shown here. Since our topic for today is about low voltage IC testing, I will start my webcast with logic level family's introduction, and then share the benefits of low logic level ICs used in the industry today. Then, we will take a look at the trend of semiconductor voltages and share two major challenges in low voltage IC testing and what are the instruments that you can use to overcome this issue. We will also discuss the demo setup and the results from this simulation, whereby you can view the actual video on YouTube. We will provide the URL at the end of this webcast. And finally, before we end this presentation, I think it is good if we can spend a couple of minutes to talk about the Agilent U8903A audio analyzer, which comes with digital option now. We will highlight the key features and the performance of these instruments, and why it is suitable for low voltage IC testing. Now, let's start with the logic level family's introduction. The logic level of digital signals is also called switching levels. They are represented by logic 0 or 1. In digital circuits of single-end signal, logic levels are usually represented by the voltage difference between the signal and the ground or some other common point. A digital transmitter drives output low voltage, usually called the VOL or voltage output low, to represent a logic 0, and another voltage called VOH or voltage output high to represent a logic 1 as shown in the figure here. Both of these VOH and VOL voltages are referenced to ground. For more common single-ended logic families such as TTL or CMOS, VOL is equal to ground. VOH is traditionally 3.3 volts or 5 volts, but in the recent years, there's a push in the industry to continue to lower the VOH in order to achieve lower power for mobile devices. So now you may ask, what is an acceptable logic level gate? Well, to understand this concept, there are a few different logic level rules that you may take into consideration. A digital receiver input low voltage, which is called the VIL over here, the voltage input low, is represent a logic level 0, and another voltage called VIH, or voltage input high, is represented by logic level 1. Normally, digital receiver high voltages are less than the transmitter high voltages, but digital receiver low voltages over here, as you can see in the equation, are greater than the transmitter low voltages. The valid input high voltage level is usually ranging from 2 volts to 3.3 volts, depending on the device that you are testing. The signal should transfer from output to input. As such, the minimum output high voltage, VOH, should be greater than the minimum input high VIH for device to operate correctly. That is, as you can see here, we have 3.1 volts versus 2 volts in order for the device to work correctly. At the same time, the maximum voltage output low should be less than voltage input low, so VOL max is less than VIL max. Signal transfer from output here to input. If it can flow from output to input, then the output voltage should be greater than input voltage. When it is at the low side, it is at the opposite, because the voltage should flow back from input to output, since electrical signal creates a loop, and if this loop exists, the device will not function properly. Based on this theory, the output high voltage must be bigger than the input high voltage as shown in this diagram. Now, let's take a look at the trend of various semiconductor voltages and logic level families that has been introduced. Over the past decade, semiconductor industry has done a great job in supplying excellent integrated circuits with higher speed, lower power consumption, and greater density. Due to different technologies, these ICs have been categorized into different logic level families. The logic level families expand from TTL to CMOS to ETL to low voltages and so on. The benefit of low logic level semiconductor devices is very attractive. We can see from the trend that is very clear that supply voltage for electronic circuits, usually labeled as VCC, has been steadily declining over the past 10 years from 5 volts to 3.3 volts to 2.5 volts, all the way down now to 0.8 volts. More and more devices are mobilized, as you know, from cell phones to MP3 players and even your tablet PCs. These devices are typically powered by batteries with power less than 3.7 volts. Some output voltage are even lower than 1.2 volts, and that's actually equivalent to just one, AA size battery. New ICs have been introduced to meet the requirement of low power supply and smaller size batteries. Based on our observation on the semiconductor industry, the trend of lower logic level is likely to continue in the industry. You can see that other semiconductor device manufacturers have similar plans to strengthen their investment on low voltage, low logic level products, and at the same time, they speed up the migration of the 5 volts and 3.3 volts logic to 1.8 volts, and then 0.8 volts, and now it's even going lower. Now, let's switch gear a little bit. This slide shows the summary of the key benefits of low logic level ICs. It can be summarized as smaller structure and higher IC density, lower power consumption or longer battery life, and reduced cooling requirements. These benefits have made it possible for PC performance to increase over 100 times over 10 years, even though the energy consumption by the PC has remained unchanged. Let's take a look at the first benefit as shown here, the benefit of using low logic levels. Low logic levels enables smaller structure and higher density ICs. The use of TTL 5 volts logic level had been the standard for digital audio signal for over 40 years. However, the increasing performance of analog to digital converter, which is usually known as ADC, or digital to analog converter, which is DAC, and complexity and functionality of digital signal processors, which is DSP, have resulted in modern CMOS manufacturing processes that produce smaller structures where the thickness of the gate oxide of each single transistor is sensitive to the electrostatic field strength. This is because this field strength is actually proportional to the supply voltage, and the supply voltage must be reduced for reliable operation of the smaller structure. Consequently, when ICs have higher density and they become more complex and smaller in structure, it's required to reduce the VCC power voltage and result in lower logic level. For reliable operation, structure size of 0.6 micron requires less than 5 volts VCC, and the use of the 0.35 micron manufacturing process requires 2.5 volts VCC for reliable operation. The second benefit that I would like to share with this low logic level is lower power consumption and longer battery life. Power consumption always is a concern for new system designs. With the reduction of the supply voltage, a proportionate power saving is observed. The chart here in this slide, as you can see, it shows the comparison of the power consumption of logic families at different voltage levels of 2.5 volts versus 1.8 volts. As you can see, reducing the power supply voltage also produces an exponential decrease in power consumption. Therefore, The trend is to reduce power supply voltages. For mobile devices, this simply means that, a much longer battery life is needed. Thirdly, low logic levels have reduced cooling requirements. The power dissipation is caused by driving an externally connected load. If we assume that power efficiency is kept unchanged, more heat will be generated with the higher power. So, the low supply voltage results in lower power consumption because, as you can see from the equation here, power is simply the output voltage square divided by your impedance of the load, and you can assume a resistor in this case. Thus, you will have a reduced cooling requirement. However, these different logic level families bring challenges to digital audio testing. Now, let's take a look at the challenges of testing low logic ICs. Today, digital ICs available on the market have so many different logic levels. If you just simply search on the web, you will find many different comparison tables and compatibility guides under different conditions. The more logic level families that are available, the more incompatible challenges occur between different logic families. This incompatibility is caused by mismatch of logic levels between the audio analyzer and device under test. All audio analyzers in the market, even some famous brands, have potential incompatibility issue because none of them allow you to adjust logic levels to match the device under test. Incompatibility may cause significant test errors as well as other measurement issues, especially when you need to design a low voltage device. Let's take a look at this example. Let's use 3.3 volts and 1.8 volts logic as an example to illustrate the problem that may be encountered due to incompatibility issue, especially when you use earlier audio analyzer models in the market. The high output voltage from your audio generator, which is your VOH over here, is normally much above the 1.8 volts of the DUT, and it's 1.2 volts minimum input high voltage. Under some circumstances, this may not be an issue, as some low voltage ICs are designed to be tolerant of input voltages in excess of their supply voltage. This may not always be the case. However, some devices may draw too much current in this situation and stop interpreting the logic level correctly, resulting in the measurement errors in the digital audio stream. For the low output voltage of the generator, in general, the output voltage may be 0.4 volts or lower. For example, 0.2 volts over here. This easily interfaces with the 0.4 volts max input voltage, VIL, of the DUT. If, however, the DUT is under very low voltage, the DUT low input logic may be lower than generator low output logic. The VOL of the generator may be above the DUT low input. This will place the DUT input in undefined state over here in this region, again resulting in measurement error. For further details, you can download our application note, and the page to download will be provided at the end of this webcast. The Agilent U8903A solves this issue with dedicated input and output logic level control circuits. So the input and output logic can be set as any value as you want. or you can select the list from the list here, or you can customize the value of your choice. This will make the logic level match perfectly between the audio analyzer and the device under test, and make the measurement more accurate and reliable. Also, as we know, low logic level ICs have limited driving capability. Hence, the U8903A digital signal input and output are well designed to not violate the DUT. After this webcast, you can download the YouTube video demonstrating the errors that can be caused by logic level incompatibility. In some cases, the errors are very significant, especially when the logic level is low, below 2 volts. Now, the second challenges that I would like to share is the issue faced when testing less than 2 volts logic level. Low logic level is clearly the trend for mobile devices today. The benefits have been stated earlier, making it possible for an IC performance to increase over 100 times over 10 years, even though the energy consumption by the IC remain unchanged. However, low voltage devices measurement will be challenging using the traditional audio analyzer, as they are designed for DUT, which operate with a power supply of 5 volts or 3.3 volts family. When testing on the new generation ICs, which could operate on a 2.5 volts, 1.5 volts, or even 0.8 volts families, these traditional audio analyzers often do not interpret the logic correctly. There will also be degradation on accuracy, functionality, and reliability. The digital audio test on low logic level has led to low quality test signal generation, degradation on the measurement accuracy, and may need to design support circuit board to condition the digital signals. The Agilent U8903A audio analyzer solves this problem with dedicated input and output logic level control circuits. So, the input and output logic level can be set as low as 1.2 volts without signal quality or measurement accuracy degradation. This is part of the digital audio output logic level control circuit. Signals are generated via the FPGA signal generator module. These signals are then sent to the transmitter chip and encoded into the required digital audio format. The digital audio output level is controlled by a 12-bit DAC, thus providing 12-bit resolution for output amplitude adjustment. The DAC output is buffered with a non-inverting amplifier and an inverting amplifier to create positive and negative signals. So in this case, we can control the logic level to any value that we want. Now, I would like to share a demonstration setup on how to test low voltages or low logic level audio ICs with the Agilent U8903A audio analyzer. This demo shows the errors caused by logic level incompatibility. In this demonstration, we are using the Texas Instruments 1772 evaluation board, and our device under test is a CS8414 chip from Cirrus Logic, which acts as a digital audio receiver embedded in this board. It is very common and can work under low voltages. Our audio analyzer here, the U8903A with AES3, SPDIF and DSI option, provides SPDIF test signal to the DUT input and the DUT output is left justified digital audio signal sent to the audio analyzer for analysis. This simulation is done to find minimum working voltage of an IC. Other instruments that you need is a power supply, as you can see here, to power up the DUT, and we are using the Agilent U8903A 60 watts dual output power supply. We also need a digital multimeter, and we are using the 34410 digital multimeter with 6.5 digits to monitor the IC power supply voltage, which is called the VDD. The first thing that we need to measure is the minimum working voltage. To do this, we will use a measurement function called audio beat, or to be more specific, working zero. We have two steps here. First, we will set the audio analyzer input logic level to 3.3 volts to simulate the traditional audio analyzer, and measure the DUT minimum working voltage. This is the common setting found on most audio analyzers in the market. Next, we gradually lower the DC output and monitor the audio beat. In this video, you can see the 0 beat stops and the voltage reading on the DMN will be shown as 1.7 volts. This means that the minimum working voltage of the IC is 1.57 volts when the input logic level is set to 3.3 volts. Secondly, what we do with this similar demonstration is that we repeat the test by adjusting the audio analyzer logic level to 1.2 volts. The second test shows that the minimum working voltage is 1.14 volts, which is clearly different from the results we previously observed. Now, let me explain further using this chart drawn based on our test results. It displays the DUT working voltage range under different input logic level. The left side of the graph, which is over here, the graph is for 3.3 volts, and this is to simulate traditional audio analyzers fixed at 3.3 volts logic level. On the right side over here is actually for the DSI input voltage of 1.2 volts, and this is set to match with the DUT output. The minimum working voltage is improved from 1.57 volts to 1.14 volts. The only thing that we did was changing the audio analyzer input logic level from 3.3 volts to a matched 1.2 volts. Let me explain why this happens. When we set the audio analyzer input logic level to 3.3 volts, as most traditional audio analyzers are, we found that the device under test stopped working at 1.57 volts. Is this really true? Not really. Actually, the device under test is still working, but our audio analyzer was not working because the audio analyzer is fixed at 3.3 volts logic level. This audio analyzer cannot interpret the logic correctly. The reason is when we lower the DUT voltage, the DUT logic level will also get lower. If we do not decrease the logic level of the audio analyzer input accordingly, the incompatibility happens and cause test errors. So in step 2, we decrease the audio analyzer input logic level to 1.2 volts, and we found out a different results. The device under test, the DUT, was still working until a much lower voltage level of 1.14 volts. If you still use a fixed logic level as most traditional audio analyzers, then you will never find out about these results. So, If your audio analyzer logic level is not adjustable, you cannot evaluate your DUT correctly. You should not be misled by your audio analyzer. We must match the DUT logic level to eliminate the error caused by logic level incompatibility. This is the only way if you want to get a correct test result. Now, we have come to almost the end of my presentation. Here is a summary of the conclusion and key takeaway from this webcast. Earlier in this presentation, you learned that there are a few acceptable logic level rules to take into consideration. Do ensure that the minimum voltage output high is bigger than the minimum voltage input high. Also, the maximum voltage output low must be smaller than the maximum voltage input low. In this presentation, the benefit of low logic level testing is also covered. Today, integrated circuits are smaller in structure and higher in density, yet it consumes lower power and does not heat up as fast as before. Based on the demonstration simulation discussion, we found that the incompatibility between audio analyzer and DUT may cause test errors to be significant, especially when testing low voltage ICs. The audio analyzer cannot provide enough or draw sufficient drain current to the DUT. This often causes test failures in a system. Some earlier audio analyzers cannot test the DUT with less than 2 volts due to hardware limitation. The U8903A is designed specifically to solve this issue, as it has the widest logic level input range of 1.2 volts to 3.3 volts and allow users to input any value within that range. Our audio analyzer has a specially designed input and output control circuit. Its input and output logic level can be adjustable in 0.1 millivolts step, so you can have an audio analyzer that matches your DUT logic level perfectly. Also, it is more powerful to draw or drain current capability with a perfectly matched DUT. It can drive any kind of DUT without lowering its logic level. This is an ideal tool to test low logic level of digital signal. Before we end this presentation, let me share an overview of the U8903A audio analyzer. The Agilent U8903A audio analyzer with digital options was introduced in September 2011. With a 2-in-1 digital audio interface card that provides speedy AES-3 and digital serial interface, or also known as DSI, the U8903A is suitable for applications such as analog and digital IC components, module design, wireless and consumer electronic audio. In IC component testing, you can use DSI to communicate between speakers and microphone with dedicated logic level control circuit built in our U8903A. You can adjust the logic level to match with the DUT perfectly and get the correct test results. The new user interface is provided together with digital audio option. You can see the logic relation among clock, data, and word visually. You can easily find any incorrect setting or mistake in measurements. This audio analyzer covers multiple digital audio interfaces, as I discussed earlier, and you can see the back panel over here showing the parts. you have the SPDIF, EES3, and also the DSI. So this gives you the flexibility to choose one or all of these options. Some digital audio ICs are designed to work in battery-operated devices, such as cellular or mobile phones and MP3 players. With a wide logic level range of 1.2 volts to 3.3 volts, the U8903A is able to support all of the current digital audio ICs. Some new measurements are also provided for digital audio tests, for example, audio bit view, bit error rate test, protocol tests for SPDIF and EES3. For those existing U8903A users, you can order a hardware upgrade to install the digital audio interfaces options. The hardware upgrade will include a digital audio card installation and calibration of your U8903A unit by our Agilent Service Solution unit. For more information on this topic, you can download the application note from our audio hints page, as shown in the slide, and you can also view the simulation video on YouTube. You can also obtain more information on our Agilent U8903A audio analyzer from the product page. And for those of you who owns the old HP 8903B audio analyzer, you can download the application note and learn how to easily migrate your codes and use our U8903A audio analyzer with greater features. Now, we have come to the end of my presentation. Thank you for your time and participation in the webcast. I will pass this back to our host and question manager, Alvin Tang.
Thank you very much, Adeline. Now it's a time for questions and answers. All the Q&A functionality is on, so you can send your questions in writing through the WebEx. All these questions are anonymous, so no one can see your name. We will do our best to answer your questions, but if we don't, we will come back to you by email. All the questions and answers will be published for others to see. We will keep your identity private. Now, you can write your questions in the question area of WebEx. There will be in the right bottom area of the WebEx.
Okay, Alvin. The first question we have, what causes the incompatibility when testing digital audio interface with audio analyzer?
Okay. Okay, let me no. Okay, as Adeline mentioned in her presentation, the incompatibility is caused by mismatch of logic level between the audio analyzer and the device under test. So when you use an audio analyzer to test a DUT, the audio analyzer in the market today, even some famous brands, have the potential incompatibility issues because none of them allow you to adjust the logic level to match the device under test. So most of the audio analyzer in the market only provide one or few logic levels. So you cannot adjust your output and input logic level exactly to meet your DUT. So this will cause the incompatibility when you're testing.
Okay, thanks, Alvin. The second question we have, what is the potential impact of incompatibility on my circuit design?
Okay. Okay, let me repeat the question. The question is, what is the potential impact of incompatibility on my circuit design? The incompatibility may cause the significant test error as well as other measurement issues. Especially when you design a low voltage IC or you design during the low voltage devices or circuit. We have an example in the video. We try to test the minimum working voltage of a DAC board in the video, and this DAC board can work at a very low voltage. The incompatibility causes about 0.43 volt error. So this error is about 35% from the real number. So you can see the error is quite significant. It's more than 1/3 of the real number. So this incompatibility will cause some critical error in your circuit design. So be careful. So when you test a circuit with a low voltage IC, so make sure your audio analyzer logic level should be compatible, should be totally, completely matched with your device under test. Okay.
Okay. The next question from our Q&A. Is there any free application to communicate with the U8903A, not VEE, something like vBench?
Sorry, Adeline, could you repeat that again?
There's a question from the audience that asks, is there any free application to communicate with the U8903A, not the VEE, something like vBench?
No, we are working on that. Currently, we do not provide the PC-based software for our audio analyzer, but by the end of this year, we will have our audio analyzer with a web server embedded. That means you can use the IE, Microsoft IE, and you can use IE to access to the audio analyzer. Then you can check the test result, and you can configure the audio analyzer. So that will be our web server function in the audio analyzer. So you can do this. You can control with this function, you can control your audio analyzer remotely.
Okay.
Okay.
One more question that we have. Why is the Agilent U8903A audio analyzer an ideal tool to test low voltage devices?
Okay. So why is Agilent audio analyzer is an ideal tool to test the low voltage device? Because the U8903A have the adjustable input and output logic level control, so it solves the compatibility issue. It has a specially designed input and output control circuit, so you can adjust your logic level in every 0.1 millivolt resolution. And we can provide a dynamic range from 0.3 volt to 1.2 volt. That's why audio analyzer, a U8903 audio analyzer, is an ideal tool for the low voltage IC design. Because another feature of this audio analyzer is that they can also provide strong driving capability. So if your DUT can draw or drain the current, then audio analyzer can provide enough current to drive the DUT. Yeah, that's why our new Agilent new audio analyzer is a good tool for testing low voltage IC. Yeah.
Okay.
Okay.
That was the last question.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM Webcast YouTube channel. Remember, all our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcast and to sign up for free, go to our website, www.agilent.com/find/web_seminars.